field that is summarized rather well in this chart, although it's somewhat imposing, right? So when I think about characterizing a material that I've made, there's many different aspects to that, right? I could be wanting to know how much of the material is there. I could be wanting to know how pure it is. I could want to know the elemental composition. I would want to know in other cases how the structures are bonded together, right? All of these things. And I would also potentially want to do that at a certain length scale, right? I would want to look at a spot that's this big, then this big, then this big, and would also be interested to understand how sensitive my method is. So how small an amount of material, not just in size, but in concentration, could I actually measure? So this chart captures all of that. We won't possibly have time to go through all of these methods. In many cases, they're extremely specialized methods. But we'll go through a few in particular that are useful for energy materials and that we use routinely in the laboratory. So this is a summary chart for different types of techniques and categories of techniques. We have, we'll cover a number of these, but structural characterization has to do with how the atoms are arranged, basically. Morphological has more to do with the surfaces, the structure and contours on a surface. And functional has to do with, in general, how the bonding is in a material. In particular, some elemental type of analysis, and in some cases, area types of measurement. So how much surface is there? And we'll go through a number of these, but all in summary form. So, excuse me, structural. The first structural technique that I'll go through is X-ray diffraction. And the words are written here, but I'll tell you more in common language what happens. When we use XRD, what we're trying to do usually is to understand the form or the nature of the bonds in the material. So what lattice structure in a crystalline material is actually formed. And you might say, well, if I have a material, don't I already know that usually? And the answer is no. There's many polymorphs of materials, and you don't always know what you made. And sometimes you can make something that's just metastable. It's not a thermodynamically stable form of the material. Diamond is an example of that, right? You know, there's a saying in the world, diamonds are forever. And it's a great ironic saying because actually diamonds are not forever. It's a metastable form of carbon. And so the point here is that you can use X-ray diffraction to tell you about how the atoms are separated from each other, and that in turn tells you what kind of atomic arrangement you have of that particular material, whether it's a pure element, a compound, or a mixture of things. So the way that it works with X-ray diffraction, of course, the name captures the major elements, right? You have X-rays, and they're diffracting on a surface. Now, you're probably familiar with diffraction of light in general, right? You know that when light hits a grating, that it will divide itself up. And the same kind of thing happens here, except in this case, we don't have a man-made grating. We have a grating that forms from the atomic arrangement. And the reason that we can use atomic structure as a grating is that X-rays have a small enough wavelength so that they are affected by the distance, the typical distances that separate atoms from each other. And so the atoms themselves become the grating. If you tried to do this with visible light, it wouldn't work because visible light has a wavelength that's many, many, many atoms long of a typical solid material, okay? So what happens here is you have an incident beam, and it comes in at an angle, an average angle, alpha, relative to the surface. So relative to the surface, in this case, the surface parallel, right? And then, excuse me, and you can you can alter that beam, that angle alpha, right? So if you had a small beam, you can control the beam angle with your divergence slit. And then you have a detector on the other side, which will scan through different angles, and we call this 2 theta, right? Where theta, really 1 theta, or 2 theta is relative to the incident beam direction and the diffracted beam direction. And you'd scan through those angles, and you pick up peaks, and those peaks correspond to lattice separation of atoms in a crystalline material. Okay? And that's what you look for in X-ray diffraction. The theory is much more complicated. You really have to go into crystallography to do that. But when we won't go through the theory, we'll go a little bit into just some examples. So what you see in this case, this is some work that we've done where we're looking at a carbonaceous material, and we have treated it with boron and nitrogen. But we start with the first part here where you have a carbon foam. You have a peak at about 26 degrees, okay? And that's a particular peak with the crystal direction in the material, right? And you might say, well, I'm seeing all these different crystal directions, crystal planes that are denoted by the terms in brackets. Why do I see all of them? Shouldn't I just see a couple? Well, in this case, we're actually using a material that doesn't have a single orientation of the crystal. This is a foam, but in many cases you'll just make a powder with your material. So you'll be seeing all these different directions because you have grains in all different directions, and that's why you see all of the different peaks. In this case, there's a dominant peak. But then what we've done is we've added boron and nitrogen to this material, and you can't really tell a big difference from the survey scan. That's the wide range of 2 theta angles. But when you look at the main peak, the 002 peak, you see that there's other content that starts to come in this area of about 25 to 25.5. That's indicative of the effects of boron and nitrogen on the carbon lattice, because you see that with the pure carbon lattice, that's the cyan colored curve at the bottom. The peak is coming out here more toward 26.5, but we're building up a shoulder, we would call that, with the boron and nitrogen. So that's an indicator. It's kind of a fingerprint of the effects of boron and nitrogen. And now I don't have a really well-defined crystalline material here, right? Because I'm actually doping the carbon with boron and nitrogen. Another technique that's similar is called XRF, or X-ray fluorescence. In this case, you strike a material with an X-ray, and instead of looking at this angle, you're actually measuring the fluorescence that comes out of it. Okay? And you can pick up the fluorescence with an optical detector. All right? And the general scheme is shown here. You have an X-ray source. You strike a material. In this case, we're showing an atom, and the fluorescence is coming from relaxed electrons. So excited electrons that relax back, and in that relaxation process, they are only allowed to go back to certain states. Those are known, certain electronic states. And when they relax down, they emit a photon, and we call that fluorescence. Okay? Here's a little bit more about how you would actually conduct such an experiment. You'd start with a solid sample typically, but you can also use liquids with this. You would subject it to an X-ray beam that comes from an X-ray tube, which are fairly easy to procure and implement. And so you have this, when you have an X-ray that comes in that has a sufficient energy to excite these electrons, right, you will then see an effect. And so you end up with looking for an electron that's excited from one of the core states, an inner orbital shell. It goes up to a higher energy state and then relaxes back. Right? That's the thing that needs to happen. So this ionized atom will relax and then transition and create with this ejected electron that comes out, in particular, it is able to then, the electron drops to a lower energy state, and out comes a fluorescent X-ray. And by looking at the spectroscopy of that, you can know what kind of material you have. Okay? What sort of element is there? So moving on to the morphological, the first morphological technique that we have, and you've heard this mentioned a bit already, it's atomic force microscopy, AFM. All right? And in AFM, it's very much like a phonograph. You have a sharp tip. Professor Kulkarni mentioned this in the last lecture. Like Mount Everest, the tip of Mount Everest turned upside down and scanning over a surface. But the hard part about atomic force microscopy is not so much making the tip. He also talked about that. There's many different ways to make the tips. At first, early in the field, they had many different techniques and some difficulties in making the tips. Now you can buy the tips from a catalog and they're usually pretty good. The difficulty with atomic force microscopy is really tracking the tip's motion, and in particular when it is influenced, when that tip's motion is influenced by different effects, different physical forces that could be at work. And so much of the activity in atomic force microscopy today has to do with going beyond just scanning the surface morphology. It has to do with maybe doing some other physical process, measuring some kind of electronic conductance, measuring some sort of extra force, long-range force that could be present in the system. So essentially what happens is you have a tip that comes down, and there's something called contact mode, okay? And you might wonder, when I'm in contact mode, am I scraping atoms away? And I guess if you're over-aggressive, you could do that. In fact, there are ways to use an AFM tip to damage the material, but normally, of course, you don't want to be doing that. So you come down and you land softly, and there's actually a repulsive regime where your tip, if you push too hard, right, there's a strong repulsion. So this potential curve that we see here should be very familiar to you, because it looks like an atomic potential curve, right? But in this case, this is the repulsion of the tip. And so you go here, and if you just get back past the equilibrium energy, or this tip surface force, then you'll be in this contact mode. Normally, that will give you a reasonable definition of the surface morphology, but there are certainly samples where you don't want to be even that close to the surface, and so you can go into something called non-contact mode, where you're more in this attractive regime due to van der Waals interactions. And in the non-contact mode, you might even be vibrating your tip on purpose, right? So that you're picking up some frequency response as well. The way that the system works, obviously measuring a deflection of sub-angstrom, which an atomic force microscope needs to do, is not easy. You could not put some kind of a physical probe on the tip to know how far it's moved, because a physical probe that can measure sub-angstrom would need to be measuring a length that's shorter than the distance between its own atoms. And so that would be extremely difficult. Instead, what you do is you use light. So you use a laser, and one of the things that has made atomic force microscopy so convenient and cost-effective now is that laser diodes have come along. Laser diodes have helped the scientific world in many, many, many different ways. And this is one of them. So that it's really easy to implement now a very high quality optical source in a laser diode, as opposed to, in the olden days, my days as a graduate student, a really big, complicated, expensive laser to do this. Now you can buy one of these lasers for, just a few bucks, a few rupees, maybe a few hundred. But you end up detecting the motion of that tip in a non-contact way. You use a laser and a detector with a bunch of optics in between. And so when the tip moves, it's ever so slightly changes the location that the beam strikes on a photodetector, on an array, a photodetector that is an array, and you read inside of that photodetector array where the peak is, and you translate that into a motion of the tip. So that's how you can magnify or leverage a sub-angstrom change in dimension into something that you could measure at the long scale, because you're basically using optics to do that, to magnify a small distance into a large distance, okay? And you end up having to do